Hello, my name is Martin Ringbauer. I'm a postdoc working at the University of Innsbruck in Austria. And on the 9th of November 1989, when the wall fell, I was in fact not born yet. As a child, I was always very curious, wanting to find out how the world works. Now I'm a physicist working on quantum computers that will soon allow us to solve problems that we couldn't solve any other way. So I guess that satisfies that itch for me. So thinking about computation in an abstract sense, we've got information going in, some calculation happening, information going out. And what we've been doing over the last couple of years is replace that calculation bit with something quantum, because that gives us access to quantum effects like interference. And that allows us to do certain calculations much more efficiently than we could do classically. For example, chemistry and physics calculations, which take up a lot of time on supercomputers nowadays. But I actually want to take a step back first and talk about the information going into the system, because before we can tell our computer what to do, we need to be able to talk to it and to have a common language. And this common language over the last decades used to be binary digits, so bits, zeros and ones. And so, to not reinvent the wheel completely, we impose the same structure on our quantum computers and teach them some zeros and ones. The problem there is just that nature doesn't care much about our zeros and ones, and the quantum systems we have access to come with a difficult energy structure with many different states. And what we do is we pick out two of these states, and we call one of them 0 and the other one 1, and we pretend all the rest is not there and doesn't cause any problems. But even if that's the case, that is severely restricting our system. And what's more is the problems that we want to study also have this kind of high-dimensional structure that we need to rewrite in terms of qubits, in terms of zeros and ones, and that again creates some inefficiency. So I would like to take a step back from this and rid ourselves of this paradigm of zeros and ones and appreciate this energy structure that we have there and see that where we put the qubit is pretty arbitrary. We could have put it elsewhere, or we could actually use the whole energy structure and encode information everywhere. And that increases the information density of our system quite a lot. And also, it allows us to directly implement these high-dimensional problems in our system without going through the inefficiency of having to rewrite it in zeros and ones. And now the energy structure that I show is not completely arbitrary. That is actually a calcium-40 ion, which is what we use in our quantum computers in Innsbruck. So this is to say that this kind of approach can be integrated directly in existing hardware. And we need to rethink the way we do computations. We need to do some engineering steps, but it is not a huge rebuilding of hardware. And quite ironically, even if you say you don't care about all this high-dimensional stuff and you just want to do your qubit calculations, even then it helps to appreciate the energy structure of the system and use it, because it gives you a cache memory within each qubit of your quantum computer. And so even then it can help to speed up things. So for the last decades, computers have been working with zeros and ones. Now with our new quantum computers, instead of using that old paradigm, we can use a more dynamic paradigm of computing, where we look at the platform we have and we ask, what is the real potential of this platform? And we look at the problem we want to address and we ask, what is the best way to look at this problem? And then we find a match and use whatever encoding suits that problem best. Quantum computers have great potential to pick up the slack where classical supercomputers give up. But getting them there is extremely challenging. And so if we can use some clever new encodings to get more out of the same quantum hardware, that takes us a big step towards the goal of using these devices to solve problems that we couldn't solve any other way. So what keeps me awake at night is the thought that we can do much better. We are teaching our quantum computers a new language, and as with every new language you learn, there's a lot of vocabulary, and of course we don't have the best way of expressing ourselves yet.